Welcome to Lecture 7a, entitled Tangential Plane and Linear Approximation to Curved Surfaces. The material for this lecture is coming from section 15.6 of the text, and the objectives are to give motivation to the importance of approximating multivariable functions about a given position, and also develop confidence in visualizing and sketching a tangential plane. The concepts and visualization skills basically covered in this lecture are an understanding of the application context of tangential planes. They come up in various circumstances, but they have different meanings. And secondly, visualizing and sketching tangential planes. Note, we briefly discussed tangential planes when we introduced multivariable differentiability in Lecture 4b, but here we go into far more detail. All right, the second slide, typically, as always the case, is just an outline of the slides to follow. And I'd like to make just a particular note of the items at the bottom here. These items 2 and 3 are not in the textbook. And so this is additional information that's being provided. Secondly, item 2a, which is this one here, is discussed in assignment 1, but you're not responsible for this material. And item 3, note 3, item 6, that's this one here, generalization for proximal multivariable function include dynamics, is discussed in assignment 2, the shorter version. By the way, this assignment 1 is the longer version. If you're interested, you can look at the shorter version, of course, does not include the information on kinematics. All right, so question of approximating curves and extrapolation to higher dimensions. What's the motivation? Well, if we're given a curve, it is sometimes of interest to approximate the curve. For example, y equals f of x near a given point, and that point would be a, and f evaluated a. A curve is in fact a 1D object in 2D space if we're talking basically about a single variable function. So what's the concept? The concept is that we can approximate a curve y equals fx at a given point, a, f at a, by a line that is tangent to the curve at the point a, f of a. And that's demonstrated by this figure here. Here's the curve described by y equals f of x, and here's the tangent line, tangent to the point a at f of a. Now we can basically expand this, the notion of a tangent to a curve to higher dimensions, but in higher dimensions basically we're dealing with, for example, in a two-variable system, a surface. So in this case we can approximate a curved surface, say z equals fx of y, which is this gray object, at a given point on the surface, which would be at this location, AB, and the z component is evaluated at AB, by a plane that is tangent to the curved surface. And that plane is this pink or purplish colored object. This is a plane which has orientation, but you have that plane just touching a point on the curved surface. So that means it's tangential at that point. So this is what we're dealing with when we're dealing with, for instance, a 2D, a 3D object, surface in 3D. Then we're talking about planes touching surfaces. You can expand it to higher dimensions, however, it'll be extremely difficult to visualize in terms of what that would look like. All right, so let's look at different contexts in which tangential planes occur. So the first is a tangential plane in a geometric sense, and this would be something that arises when we're dealing with kinematics, for instance, objects rolling down a hill. All right, this is covered in this particular lecture. You're not responsible for this because the details of this are in archive reading assignment 1, but this includes details that are not in the shorter version. But for those that are interested, they can always look at it. So what's the idea behind this? First of all, near a given point on a curved surface, given by z a function of x and y, the surface can be assumed to be planar in a small vicinity around a given point. The plane which just touches the curved surface at the given point on the curved surface is referred to as the tangent plane. Now, the motion of an object on a curved surface can be decomposed into a component of motion normal to the plane and two orthogonal components of motion tangential to the plane, t, at any given point on the surface. So if you look at this diagram, Here's the motion of the object, just to presume for time being it's some motion. The vector basically that's parallel to the direction of motion is the unit tangent vector. The normal vector, which is this n, is this normal to the surface. And you would ask yourself, well, we sort of are interested in what this one's doing. This one is defined by the surface, but we need one additional vector to define motion in 3D. Well, we can obtain the third orthogonal vector by taking the cross product between the normal vector and the unit tangent vector. So that's shown there. And so this is what you would do at each point on the surface, and you would end up deriving a set of differential equations describing the motion of an object on a curved surface. All right, second would be time-independent physical models, also called sensitivity analysis. That's covered in this lecture. And so let's just go through quickly to describe what this is. A multivariable function can describe a physical relationship between output variables and input variables. For example, cost is a function of losses and efficiency. So that would be, for instance, if you're designing a power supply, efficiency would be important because essentially higher efficiency means less heat and also a lower operating cost. Losses basically are things typically that go into heat. Second is wish to know how small changes in the input variables, which would be efficiency and losses in this example, impact the output variable, in this case the output variable is cost, and this is referred to as a sensitivity analysis. The function, which is cost as a function of loss and efficiency, is a curved surface. It's approximated by a tangent plane at a given operating point. The operating point would be efficiency, losses, and the corresponding cost for those 2 points. Frequently, it's convenient to make input and output variables unitless. We call this also a per unit analysis to compress the range of numbers. It just makes things sometimes from a calculation point of view much easier. Now this diagram below just shows you an example. This is the losses along one axis, efficiency along another, and the cost along the z-axis. These are per unit. In other words, the losses will be divided by some nominal value so that the ratio has no units. Similarly, for the efficiency already is unitless. Now you'll notice here 2 points, 2 operating points, one here and one here. And let's say we take a small region around that. In other words, we're interested in knowing what happens if we move in this direction or this direction away from this operating point. Similarly, this is a different operating point. What happens if you make small changes? Well, if you take this and determine what this would look like projected onto the actual surface, then this would tell you basically for small changes either in losses or efficiency that would result in certain changes in the efficiency. And so this is, for instance, at this point, you might have certain changes, whereas in this area, perhaps the changes are not as significant. Anyways, you can look at this in more detail if you want by just clicking on this URL here. All right, just some examples of the multivariable functions to be approximated at a given point. Here's an equation of a sphere in implicit form. We could have also written this equation of a sphere in explicit form. However, we would have to represent the sphere in terms of a hemisphere. 2 hemispheres, one of them defined by a positive square root and the other one defined by a negative square root. In implicit form, that's not necessary. An objective, for example, might be to determine the tangential plane at a given point x0, y0, z0 on the surface of the sphere. Second example would be, for instance, if you're determining the cost as a function of mass and say footprint meaning the physical area that an object holds. This would be an explicit form of an equation. And here the objective would be to determine the cost sensitivity as a function of small changes in mass and footprint about a nominal value of mass and footprint. All right, so now let's consider the motivation to approximating multivariable functions that include dynamics, which means that we're saying that something is a function of time. In this case, we're going to be looking at a single input and an output example. The graph on the left at the top here basically shows a relationship between y and x. X we're going to call a state variable, y we're going to call the output. And we're going to be looking at what happens to y as we vary x about this operating point q, which has coordinates capital X, capital Y. And so what we would be doing is writing that the output Y would be Y plus a perturbed value, which is a variation of Y, which would be equal to G evaluated at the unperturbed value of X, which is equilibrium point, plus a perturbation in X, and this would be a function of time. If we then look at the graph on the bottom left, what we would like to do is to approximate this curve by a straight line, which is a tangent line tangent to the point Q, which again has coordinates X and Y. And so if we make a variation X back and forth, then we would expect to see a variation of Y about this equilibrium point Q. And so the diagram here indicates how that would be basically sketched. So we'd be making a change in X, which is this red sine wave we see here. And we're just going to basically have a periodic value. And so X is varying to this point and then varies back to this point. But to show that it's a function of time, we're basically expanding out a sine wave in this direction. This direction represents time. So if this is how X varies, then we can basically show how Y would vary using this straight line approximation. So for example, this point here would represent this point that you see here. It's the peak of this blue sine wave. And this minimum point that you see here would represent this minimum point that you see here on this blue sine wave. And so over one cycle of the input, you can see there's a cycle of the output. And we'd like to know what the relationship is between this sine wave and this sine wave. So objective is that the output is equal to y hat t, where typically this would be delta y. But since we're dealing with time variation, we basically define delta y as being y hat t, where y hat indicates small. And the input basically is x of t hat. And again, because x is small and time varying, we don't use delta x, we use x hat t. So now let's look at how this is in terms of an example. One state variable and one output variable. So we're going to consider the following example. Y is equal to g of x, and let g of x take on this form. This is the shape of the curve. And we're going to replace x by the equilibrium value plus a perturbed value about the operating point, but it's basically small change with respect to time in the value of x. And here again, t is time, x is a state variable, y is an output variable, and capital X is a constant. So the question is, how does y vary as a function of time? That means small signal for y hat t, if x of hat t is very small in comparison to capital X. So we have basically 4 steps to consider. The first step is to expand out y as a function of time. And so first of all, I say that y is the equilibrium value plus a perturbation with respect to time. And that's equal to the function g evaluated at the equilibrium point, but perturbed by a certain amount in the value of x. Again, this is a function of time. So this is a small signal x. Again, the operating point is xy. All right, step 2 is to expand out the right-hand side, that is this side here, in the form of a Taylor series, and retain only terms up to and including first-order derivatives, and evaluate the expression at the operating point. So g of x plus x of hat would basically take on this form to first order. You have the value of g evaluated at the equilibrium point, the derivative of g with respect to x, and then evaluate the equilibrium point, times x hat t. So if we now basically take the value for g, take its derivative, and substitute for x equals x, then basically we have the expression that you see here. And so here, the last basic thing to do is to make the substitution, and this is the form of the expression that we get. Step 3 is to equate the left-hand side with the right-hand side. That's basically this with this, and so this is what we've written here. And then finally, the last step is to determine the small signal y hat t. And y hat t basically will just be equal to the term that precedes x hat t, since y equals g of x. This basically is the equilibrium, so when you bring this over to the other side, y minus g of x is 0, and so you're just left with y hat of t is this value times x hat of t. Okay, so the next step now is to generalize what we did for the single variable case where there were no time dynamics associated with the problem. And so now we have the more general case, which is to approximate multivariable functions that include dynamics. And so I'm going to start with what we call a system model. And what I have here basically are what I'm going to call state variables. And these state variables are typically associated with a differential equation, which describes the behavior of a system under dynamic conditions. So for every differential equation, you have a state variable. So if there were n differential equations, there would be n state variables. You also have inputs into this system model, which we'll designate by U with subscripts. And I've shown here that there are m inputs. So that could be, for instance, a voltage that's perturbing the system. It could be a current, could be various things. You also have outputs. In this case, I say they're up to k outputs. And this output could be output across voltage across a resistor. It could be the power loss in the resistor. Anything that you could possibly dream up, but could be an output. And so this is a generic problem. You put some inputs, you have dynamics, and you have some outputs. And so I've summarized these points here in terms of input variables, output variables, and internal variables, also referred to as state variables, that are determined by the dynamics of the system. All right, so this is item 3 that then we'll be dealing with, but this is going to be in class 8 where we look at the details. But for now, let's look at some general principles. So we call this small signal modeling that we're going to be doing. So we have output variables y1 through yk, which can evolve with time in response to small signal variations in the input variables, that is u1 through um, and the state variables x1 through xn. At a given operating point, these operating points would be essentially where you are basically driving the system with a steady state value for u1. It could be, we call it sometimes steady state, equilibrium point, and so on. And so each one of these would have steady values that you're putting in. And as a result, you're going to end up presumably with steady values for x1 through xn. And as a result, you're going to end up with steady values for the outputs as well, which generically are determined by the state variables and the input variables. All right, so this is more or less, determining the steady state characteristics of the system. The dynamics of the system is governed by coupled or decoupled differential equations involving state variables x1, xn, and the input variables u1 through um. And so if you'll notice here, this is a generic form for a differential equation. This would be dx subscript n. This would be, for instance, up to n differential equations, each having a functional form on the right-hand side that involves potentially all of the state variables as well as all of the input variables, but not necessarily the case. And so you would have n such equations with right-hand side expressions all being in general different. All right, so let's look at some examples illustrating a set of system equations, and then also finally derive what the actual objective is. So if we have, for example, a case where there are 2 state variables and 2 input variables, this is just an example of an equation that we could have. You have a differential equation in the state variable x1 and one for x2. And this involves x1 squared, x2, u1, and u2. The fact that this term is not linear in the state variable means that this differential equation is a nonlinear differential equation, whereas this is linear in all variables, state variables and input variables, so this is a linear differential equation. Typically, these 2 equations would have to be solved concurrently, simultaneously, and for the most general of problems, there is no analytical solution and would have to be solved numerically. The output equations could, for example, take on this form. So you'd have one output, for example, which is some function of both state variables and both input variables. And similarly, the output y2 could be a function of both state variables and input variables. Notice here that the term u2 of power 4 is a nonlinear term. And so this output equation would be a nonlinear equation, whereas this output equation is a linear equation because it's linear in the state variables as well as the input variables. So just to summarize, in this case, the state variables are x1, x2, associated with the derivative. Input variables u1, u2, and output variables y1, 2. So the next thing would be to establish the operating point. And operating point would be if you hold U1 steady, that means U1 at some U1 capital and U2 at some U2 capital. If you do that, that means that under steady state condition, there can be no time variation in the state variables. If there's no time variation, that may mean that the state variable derivative with respect to time would be equal to 0 for this one as well as this one. So in the end, what you end up with are two algebraic equations. You have the input variables, which are fixed at whatever the equilibrium value is. And you have two state variables, x1, x2, and two equations that need to be solved in order to determine the steady state or equilibrium values for both x1 and x2. Now, if these were linear equations, there are obviously techniques for solving them. If it's a nonlinear equation, essentially it's quite difficult, and most often you have to resort to numerical means to establish what the value for x1 and x2 would be under equilibrium conditions. The other caveat is that for nonlinear algebraic equations, you could have multiple solutions, not just one solution or no solutions. So just keep that in mind. Okay, so again, basically, as you stated, nonlinear in an input variable here and nonlinear in a state variable here. All right, so the objective would be to investigate the small signal dynamic behavior of the state variables, that is, how do they change as a function of time, as well as the output variables in response to small signal time varying variations or perturbations in the input signals, which means U, about an operating point being the steady state values or equilibrium values, which would be U1 equals U capital 1 and U2 equals U capital 2. All right, so just a little bit more in terms of conditions under which a tangential line and tangential plane can exist. We've discussed this when we discussed differentiability, so we'll just revisit the subject. The function, so let's look at the one variable function case and then look at the two variable function case. So in this case, the function y equals f of x must be differentiable at the point of interest if we're going to basically have a tangential line. So the example that you see here, it's clear it's a smooth curve, and so a tangential line exists. In contrast here, you can see there's a cusp at the point top, which means the slope of the curve basically changes abruptly at the cusp, which means at that point, function is not differentiable. Now let's expand the notion of tangent from 1D to 2D. So if we have a curve, it's basically we call a line. If we're dealing with a surface, it's a curved surface. If we're dealing with a tangential line for one variable, then we're talking about a tangential plane for two variables. And this can be extended to higher dimensions. So if we look here, for instance, you have a smooth surface and you have this tangential plane which just touches at some point on the surface. That's by definition what we mean by tangential plane. On the other hand here, you'll notice it comes to a point. And so if you were to basically try to fit a tangential plane at this top point here, it will not be possible. So this one will not be differentiable, whereas this is differentiable. Okay, so next would be visualization of the tangential plane. So on the left here, basically, this is a 1D, a one variable case. So this is going to be just a linear approximation about this operating point. So even if I were to take this curve and just investigate how it changes in the limit, in this area would be basically a straight line. And this red line is in fact the tangential line to the point at A, f of A. Extending this to two variables where we say a tangent plane is tangent to a curved surface, we'd be looking at the position at this point here, which is AB, f evaluated AB, and the tangential plane basically will be linear in x and A. We'll just touch at this point on the surface. So this is, again, a more of a diagrammatic view in terms of if we looked at a tiny little section at this point on the surface and investigate what the surface features looks like. We can see that it looks curved, but if you make it smaller and smaller, then this approximates that of a flat surface. All right, so there are a number of interactive visualizations of a tangential plane you can look at. This is example 1. So you can basically play with which octant you want to look at. You can zoom in You can look at basically a number of things in this particular example. Second example, there's another one. Here basically, again, you can play with which octants you're interested in. You can even choose a point of operation in the XY plane, right? That is the position that you're interested in at the surface. You can see also there's a blue vector which indicates the normal to the surface. And the red vector would be tangential to a particular curved line. Anyways, you can investigate this in more detail if you wish. All right, so that basically concludes Lecture 7A. Thank you for listening.